Hello, my name is Patrick Gibson, and welcome to my presentation of the CH223 Spring 2021 project. For my project, I chose an electrochemistry exploration, which is specifically making a battery at home. So I found this question to be really interesting because we use batteries every day in our lives, yet we don't really have a great understanding of how they work. Since we studied electrochemistry in CH223, I thought it'd be interesting to try to make one ourselves. Our hypothesis then is that using our knowledge of electrochemistry, can we make our own batteries using commonly available household items? I want to talk a little bit about the background of what we learned in CH223 that will lead us into the experiment design for this project. So this is a galvanic or voltaic cell. It has a bunch of different elements, primarily the anode and the cathode, which function as the positive and negative terminals of the battery. There's a wire that goes between them, which we can use to measure voltage on. And there's an electrolytic solution that both the cathode and the anode are dipped in, as well as a salt bridge to facilitate the transfer of ions between the two different half cells. Our experiment design is going to use one of the more classic galvanic cell designs, which is a zinc anode and a copper cathode. Unfortunately, in this classic design, they use a zinc 2+ solution and a copper 2+ solution. Finding zinc and copper at home is easy, but finding zinc 2+ solutions and copper 2+ solutions is not. So we'll have to substitute something for those, and we'll talk about that in a little bit. So the way this battery works is that our zinc acts as our anode, meaning it oxidizes in the zinc 2+ solution, and it gives off electrons, whereas copper is reduced in the copper 2 solution. When copper gains those electrons that come in over the wire from the zinc, it absorbs the copper 2+ ions in the solution and creates more copper. Now, the classic version of this battery experiment is quite different from the idealized galvanic cell. First, it uses coke as an electrolytic solution, and second, it does not separate the half cells into two different cells. It just uses one cell in a single cup. So that means that there is no salt bridge in play. In my opinion, this experiment lacks the scientific nuance needed to recreate a galvanic cell, and so I wanted to strive to do something a little bit more faithful to the original design. In my design, we do use two different half cells, both using Dr. Pepper instead of Coke, but we also use a salt bridge using Epsom salts to provide a proper electrolytic solution for which the ions to flow through. I also use a zinc-plated bolt as our anode and a copper washer as our cathode. Now, Dr. Pepper has a very low pH, about 2.9, so it's very acidic. This allows the zinc to oxidize. Epsom salts, on the other hand, contain magnesium sulfate, which allow ions to pass through uninterrupted. So here are a few photos showing the creation of the salt bridge. I basically used some plastic tubing as well as some cotton balls to create stoppers at the end and filled it with the solution. Here's a setup of the experiment where you can see the zinc bolts and the copper washers. It's producing 0 voltage. And here we've added the salt bridge, which allows the electrons to flow and the ions to cross over the salt bridge and a recordable voltage to measure. I was also able to chain these cells in series so that we could actually increase the voltage. So our battery works, but how do we interpret this data? First and most importantly, we were able to get a usable voltage, which is great. I did notice that the voltage was constantly dropping, which may be due to the fact that there were many uncontrolled reactions happening at once, thanks to us not using pure solutions of copper 2+ and zinc 2+ ions. There were also many other environmental factors, such as temperature and pressure, which led to deviations from what we would expect the voltage to be given standard reduction potentials. Finally, there's also the question of how oxidation of metals played into this and whether or not the copper had oxidized too much or not enough before being reduced. So, to wrap up, in conclusion, we were able to make our own battery at home using easily available household items with some limitations on our expected voltage. I've included here some references. And I wanted to thank you all very much for your time.